Hello, students. We have got problem 10 here with a cuboid. I have always called this a rectangular prism, but apparently we can call it a cuboid. So there you go. O, A, B, C, D, E, F, G. Square base of length 2 and a height of 4. P and Q are the midpoints of E, F, and F, G. All right, let's start labeling some stuff here. So P is the midpoint of EF, and Q is the midpoint of FG. Okay, there we go. Beautiful. And what was the measurements? Square base of length 2 and a height of 4. So let's just throw a couple coordinates down there then. This means that the point B is 2, 2, 0, for example. The point P is a midpoint, so I guess it's um, one step in the X, two steps in the Y, and we had a height of 4. So that looks correct to me. And then similarly with point Q, let's see, that looks like it's 0 steps in the X direction, 1 step in the Y direction, and 4 steps in the Z direction. And what are we trying to do through the points A, P, and Q? So I guess I didn't really need to label B, but that's fine. Point A is 2, comma 0, comma 0, and we have everything we need. So when you're finding a plane and its Cartesian form, there you're going to want to find some vectors and do the cross product of those vectors. And so it looks to me like we could do AQ and AP or QP. As long as you're using all 3 points in your vectors, you're going to be okay. So I'll just do AQ and then I'll do a P. That way I am using both of my points there. I'm going to pause for a second. Looks like I'm low on battery. Pause. Right. So AQ is, we went down 2, we went up 1, we went up 4, we went AP. Looks like we went down 1, up 2, up 4. So now you know what we're going to do. We're going to cross product those because we want to find a vector that is normal to both of those vectors so that we can write our plane equation. And I really hope this pops out to be, pause it again. All right, take 3 here. So we're doing the IJK thing. It should feel pretty familiar by now. We have I times 4 minus 8 minus j times negative 8 plus 4, and then plus k times negative 4 plus 1. I believe I did that correctly. And so that pops out to be negative 4. That's going to be double negative 4. And that's going to be negative 3. Okay, and so that's my normal vector. I'm going to slide that thing up here and do the normal vector. And when you do the plane equation, you're dot producting the normal vector with your arbitrary vector in the plane. So x minus any x coordinate, y minus the y coordinate, z minus the z coordinate. I'm going to use point A as my arbitrary point because it's got some zeros. So I think it's the easiest one to use. So I'm going to dot product my normal vector, negative 4, 4, negative 3, with x minus 2, y minus 0, z minus 0. And then that's going to equal 0 because the normal vector has to be perpendicular to any vector that is in the plane. So after all that fun stuff, we get negative 4 times x minus 0 plus 4 times y minus 0. So I'm just going to write y minus 3 times z equals 0. And then distributing out, we get negative 4x plus 8 plus 4y minus 3z equals 0. Then I look at the desired form that they had, and when I look at that, they have a positive x. And so I'm going to move the 4x and the 4y and the 3z to the other side, and I get 8 equals 4x minus 4y plus 3z as requested. Bueno. So now I'm going to delete everything because I already have the answer right there. Find the equation of the line that carries the space diagonal BG. Okay, so B is the point 2, 2, 0. G is the point 0, 0, 4. There are a few different versions that I could write this in. I'll just first find the vector BG, although you could have done GB and it would work just the same. So BG goes down 2, up 4. So one version of the form of the equation is that all vectors that are on that space diagonal, they start somewhere. We'll just use point B, and they move in the direction of BG with a parameter of t. So that is the equation of the line written in vector form. You could also, of course, write that in parametric form, that x is equal to 2 minus 2t, y is equal to 2 minus 2t as well, and z is equal to 0 plus 4t. And you could also then solve each of those components for the vector t and get your Cartesian form, which I guess would be x minus 2 over negative 2 equals y minus 2 over negative 2 equals z over 4. Okay, so great. However you want to write it. It didn't specify, it just said find the equation of the line. I guess if I was being super picky, I would say that the vector form is a single equation, and so is the Cartesian form, whereas the parametric form is 3 equations, but they weren't very specific. So I will accept any of those versions of the form because they all demonstrate the same amount of understanding. Okay, letter C here. Determine the angle between the plane APQ and the line BG. So whenever you're doing angle between two things, you're thinking of the dot product, you're thinking of cosine theta. So we're going to do the dot product. So we're going to take our normal vector from the plane. It's right there, 4, negative 4, comma 3. And we're going to take our direction vector. It's right there. And we're going to dot product those. So 4, negative 4, 3 dot negative 2, 4 is going to come out to be negative 8 plus 8 plus 12. Did I do that right? Yep, so that equals 12. So the dot product is 12. Now we do our magnitudes. So the magnitude of the plane equation's normal vector, so the magnitude of this is 16 plus 16 plus 9, because that's 4 squared and 4 squared and 3 squared. So what does that make? 32 square root of 41, I believe. And then the other vector's magnitude is 2 squared plus 2 squared plus 4 squared, magnitude of 24. And then remember that the formula that I'm going to be using is that the cosine of the angle is equal to A dot B divided by magnitude A, magnitude B. And so what do we get? The cosine of our angle is 12 divided by the square root of 41 times the square root of 24. So grab a calculator and do the inverse cosine of 12 divided by square root of 41, square root of 24, and that gives me approximately 1.178, and that's in terms of radians. Now be careful, because what I just found was the angle between the line and the normal vector of the plane, and so that would be complementary to the plane itself, and so we can just subtract the angle we just got from 90 degrees. And so I'm going to subtract it from pi over 2, and I get 0.392. So this was I'll put a little n here, that's the normal theta. And then the actual theta that we are asked about is approximately 0.39, I guess 3. happens there. And there you go.